So, have you ever wondered how a computer can predict something like the price of a house or forecast a company's sales? Well, a lot of the time, the magic behind it is a tool called linear regression. And today, we're going to break down exactly how machines learn to, well, predict the future. It really all boils down to a pretty simple question. Can we feed a machine a ton of information, say about houses, and then have it make a really smart guess about the price of a house it's never ever seen before? Well, the answer is a big yes, and you might be surprised at how intuitive the method actually is.
Okay, so before we can get an answer from a machine, we have to be super clear about the question we're asking. Because as it turns out, in the world of machine learning, there are really two main types of questions you can ask.
And this is a really fundamental split in machine learning. On one side, you've got regression. That's when you're asking, how much? You're trying to predict a number on a continuous scale, like a price. On the other side, you have classification, which asks, which one? Here, you're trying to pick a label or a category, like, is this email spam or not spam? For today, we're going to stick firmly in the world of regression. So, okay, how does the machine actually answer that how much question? Well, the whole idea behind linear regression, which is kind of the simplest form of this, is actually really elegant and super visual. Okay, I want you to picture this. Imagine you take every single house you have data on, and you plot it as a little dot on a graph. On the bottom axis, you've got its size, and on the side axis, you've got its price. What you'd end up with is this big cloud of dots, right? Just like you see here. Well, linear regression is basically the art of finding the one single straight line that cuts through that cloud of dots in the best way possible. And that line becomes our prediction machine. But wait a second. Best? What does best even mean? I mean, that sounds kind of subjective, right? But for a computer, for math, we need a rock-solid, precise definition. So how in the world do you measure if one line is better than another one? Well, we figure out what's best by measuring what's wrong. For every single one of our dots, our actual houses, there's a little gap between it and the line we drew. That vertical gap is called an error, or a residual. The best line, then, is simply the one that makes the total of all those little error gaps as small as humanly, or I guess mathematically possible. And to give this a proper name, we use a score called mean squared error, or just MSE. It sounds complicated, but it's not. For every single point, you take that error, that little gap, and you square it. Now, squaring it is clever for two reasons. One, it makes all the errors positive, and two, it really punishes the big errors way more than the small ones. Then you just add them all up and take the average. That's it. The computer's entire job is to find the one line that gets that MSE number as tiny as possible. All right, so we get it. The goal is to find the line with the lowest possible error score. But how does the computer actually find that line? I mean, it doesn't just guess a billion times, right? No. It uses this really cool and, believe it or not, intuitive process. And the best way to understand this process is with a little analogy. Okay, so I want you to imagine that every possible line has an error score, right? Now, instead of thinking of those scores as a list of numbers, picture them as a landscape, a giant 3D bowl, just like this. Every point on the surface of this bowl is a different line, and how high up it is represents its error score. So the lowest point, way down at the bottom of the bowl, that's our perfect line, the one with the absolute minimum error. So what does our computer do? It starts somewhere random, high up on the rim of the bowl. And to get to the bottom, it does what you or I would do if we were hiking in the fog. It feels the ground right where it's standing to see which way is steepest downhill, and it takes one small step in that direction. And that's literally what the machine does. The process is called gradient descent. Here's how it works. Step 1, start with a totally random line. Step 2, calculate its error. That's basically figuring out how steep the slope is at that point in our bowl. Step 3, nudge the line just a little bit in the direction that makes the error go down. And step 4, repeat. It does this over and over and over again thousands of times. Nudge, check the slope, nudge again, until it finally takes a step and realizes, hey, the error isn't getting any smaller. That's it. It's found the bottom of the valley. Okay, that's enough theory for a minute. Let's get our hands dirty and see how this actually works in the real world. We're going to apply this to a classic problem and see what this thing can really do. So we're going to be working with a famous data set, the 1990 California census data. We're talking about information on over 20,000 neighborhoods here. And for each one, we've got all sorts of juicy details. Stuff like the median income in that area, the average number of rooms in the houses, how old the houses are,
You get the idea. And our mission, should we choose to accept it, is to predict the median house price for each neighborhood.
So after our model does its whole gradient descent thing and finds that perfect line, what does it give us? It spits out these numbers, and they're called coefficients. The easiest way to think about a coefficient is like a little dial for each feature. It tells us how much that feature pushes the final price up or down. And look what our model figured out. It learned that for every 1 unit jump in median income, the predicted price shoots up by 65 grand. Whoa! It also found that each extra room adds about 20,000 bucks. And kind of makes sense. For every year a house gets older, the price dips by about $200. And this right here is the real magic of linear regression. It's not some mysterious black box. It doesn't just give you a number and say, trust me. It gives you a model that you can actually understand. We can peek under the hood and see why it's making its predictions. And that little phrase, holding all other factors constant, is so important. It means we can see the pure impact of just one thing at a time, which is incredibly powerful.
But, like any tool, it's not a silver bullet. You can't just throw linear regression at every problem and expect it to work. It's powerful for sure, but it comes with a rule book. There are some really important assumptions we have to know about.
Yeah, for this whole thing to work, the real world kind of has to play along. First off, it assumes the relationship is a straight line. I mean, it's in the name, right? Linear regression. If the real connection between, say, size and price is actually a curve, our straight line is going to be wrong. It's also super sensitive to outliers. Think about it. If you have one crazy expensive mansion in a neighborhood of normal houses, that one point can literally pull the entire prediction line up, messing up the predictions for everybody else. And finally, it gets really confused if two of your inputs are basically telling it the same thing, like number of rooms and total square feet. The model can't figure out which one is really important, and its results can get a little wonky.
And that really brings us to the big takeaway here. Linear regression is absolutely fundamental. It's fast, it's efficient, and most importantly, it's interpretable. You can understand why it does what it does. But at the end of the day, it's still just a simple, straight line trying to navigate a really complex, messy, and often curvy world. So the real skill here isn't just knowing how to use the tool, it's developing the wisdom to know when that beautiful simplicity is exactly what you need and when you need something a bit more complex to capture the true picture.